Hi, my name is Oktay. Welcome to today's video about the chemical element barium and the world of superconductors. This is a picture of the element barium as a metal in an argon atmosphere. Barium has the atomic number 56. Its name comes from the Greek word baris, or baris, which means heavy. And in nature there are only barium 2+ ions. You can see there are 6 isotopes in nature plus one radioactive isotope, 130 barium. Most common isotope is 138 barium. This is a picture of the periodic table and the nucleosynthesis of the chemical elements. Barium is here. It is a member of the alkaline earth metal group, and its origin is from dying stars and merging neutron stars. The soluble compounds of barium are very toxic. This is a picture of the abundance of the chemical elements in Earth's crust. Barium is at number 14 with 0.04%. So it's quite abundant here. About the same as strontium and about the same as lithium. And these are two important barium minerals. That's at the left barite, barium sulfate, and at the right witherite, which is barium carbonate. This gentleman at the left, Carl Wilhelm Scheele, discovered barium oxide, BaO, in 1774. And the gentleman at the right, Sir Humphrey Davy, isolated barium metal in 1808. By electrolysis of barium oxide together with mercury oxide. And the name barium was given after the mineral barite. This is a picture of highly purified barium. This is how you can make barium metal. Starts with barite. It is reduced with carbon, makes barium sulfide. A reaction with water and carbon dioxide, you get barium carbonate, which is heated. When it loses carbon dioxide, you get barium oxide. And the last step is aluminothermic reduction of barium oxide with aluminium. That makes barium and barium aluminate. And the barium metal can be separated by vacuum distillation. Important compound is barite, barium sulfate. World production in 2022 was number 1 producer India with 2.6 million tons. Number 2 China, number 3 Morocco. This is one of the uses of barium as a getter. This is the getter, cup-shaped device with that contains the barium powder. And you make use of the fact that barium reacts with the compounds of air. And this barium getter helps maintain the vacuum in a vacuum tube. There's another use, spark plugs, which contain an alloy of barium and nickel. You get a more efficient burn with barium, and the barium reduces the emissions of nitrogen oxides. These are compounds that can be used for green fireworks. At the left, that's barium chloride, which gives you a brilliant green color. And at the right, that's barium nitrate, BaNO3, which gives you more apple green or yellowish color. This is a barrier, which is barium oxide, BaO. It was used in cathode ray tubes. And it is a component of crown glass, which is used for lenses. And one example is BaK4. That's a barium crown glass that is used for binoculars. This is barium sulfate, BaSO4. It is not soluble in water and therefore not toxic. And the reason is its high lattice energy. The barium and the sulfate ions fit nicely together, build a very stable structure. and the water molecules cannot break the structure. 80% of the world's production is used for oil well drilling fluid. And BaSO4 can also be used as white pigment for paints, plastics and rubber filler, for pyrotechnics, and in the copper industry. This is another use of barium sulfate. It's called barita or barita. It is a thin layer of BaSO4 on paper. This was invented in 1884 in Germany. That gives you a better opacity, brightness, and gloss. The colors become more brighter and sharper, and the amount of ink needed is reduced. This is another use of barium sulfate, very important as a suspension. You can drink it, and barium sulfate functions as an X-ray contrast agent. And you can do that because of, it is not toxic and it has a high density. That's why barium sulfate is on the list of the World Health Organizations of essential medicines. There's another important use of barium compounds as a Lindlar Catalyst, which is palladium deposited on calcium carbonate or barium sulfate. And this catalyst is poisoned with lead or sulfur compounds. Poisoned means you change the catalyst, you make it less reactive, but at the same time the catalyst becomes more selective. The Lindlar Catalyst allows you to a partial hydrogenation of alkynes to alkenes, but not to alkynes. So you can reduce this triple bond to a double bond, but not further to a single bond. And these are two examples. At the bottom, this triple bond reduced to a single bond, a double bond. And this is a surface reaction. That's why you get this isomer. This compound is maleic acid, but not the transform. And this Lindlar catalyst is important because it is used in the synthesis of vitamin A. There's another important compound, ZBLAN, which is fluoride glass. It allows you a continuous transmission of light from UV wavelengths to mid-infrared wavelengths. This compound was found in 1974. It is a fluoride of zirconium, barium, lanthanum, aluminium, and sodium. And this group of compounds can be used for optical fibers, and this is still a subject of active research. This picture at the left, that's fluoride glass, which is doped with praseodymium. In the middle, it is light pinkish color with europium, 3+ doped. And the right version is pure ZBLAN. This was a big scientific sensation. YBCO, barium copper oxide. This was the first high-temperature superconductor, which means its critical temperature is above 77 Kelvin, which is the boiling point of nitrogen. And for this discovery, the Nobel Prize in Physics was given in 1987 to Georg Bednorz and Carl Müller. You can see the superconductive material floating over a magnet. This is the structure of this compound, yttrium barium copper oxide. This X is important. This kind of structure with the general formula ABX3 is called a perovskite structure. You can see ribbons of COO2 and planes of COO4. Barium is here, yttrium is here. And the point is, this is a non-stoichiometric compound because 2/9 of the oxygen positions are unoccupied. This is important for this property as a superconductor. This is the theory that explains superconductivity. It's the Bardeen-Cooper-Schrieffer theory. And for this theory, in 1972, the Nobel Prize in Physics was given to John Bardeen, Leon Cooper, and John Robert Schrieffer. Electrons are bound by phonons. Phonons are quantized sound waves, and you get these Cooper pairs. And the Cooper pairs can travel through the structure without loss of energy. And superconductivity is a phenomenon at low temperature, because then the atoms move very slowly, very little, and the electrons can get through, and that's why you have superconductivity. However, this BCS theory cannot explain the high temperature superconductors. This group of compounds challenge this theory. The phenomenon of superconductivity was discovered by this gentleman, Heike Kamerlingh Onnes, in 1911, with the element mercury at below 4.2 Kelvin. In the middle, that's his original diagram, the resistance and the temperature. So below 4.2 Kelvin, the resistance is 0. And Kamerlingh Onnes immediately recognized the importance of this discovery. These are his words. Mercury has passed into a new state, which on account of its extraordinary electrical properties may be called the superconductive state. For this discovery, a Nobel Prize in Physics was given in 1913 to Heike Kamerlingh Onnes. And he also was the first person who produced liquid helium. And this led to the discovery of superfluid helium-4 at below 2.2 Kelvin in 1937 by Kapitsa, Allen, and Meissner. At the right, that's the picture. Superfluid means it has no viscosity. It can automatically creep over every wall until all these heights are equal. And this is a picture of the Meissner-Ochsenfeld effect. Once the temperature goes below the critical temperature, magnetic fields are expulsed, and this magnet starts to float over the superconductor. This is a very interesting superconducting temperatures diagram of with the periodic table, and you can see all the superconducting materials elements. Green is at ambient pressure, blue is at high pressure, and you can see very interesting, for example, lithium becomes a superconductor, but sodium, potassium, rubidium not. And mercury, lead, niobium, vanadium, these have quite high critical temperatures. And some elements become superconductors only at high pressure, like sulfur at 17 Kelvin, or silicon, germanium, bismuth. It's very interesting. This is a timeline of the discovered superconducting materials. You can see this is a big range of groups of materials. And y-axis is temperature, x-axis is time, or a year of discovery. You can see some elements become superconductors, mercury, lead, niobium, or some alloys like niobium, germanium. And you can see the jump with the discovery of the YBCO superconductors. And these compounds also superconductors, for example, hydrogen sulfide, but only at high pressures. And here is room temperature. For example, other compounds are 360 fullerenes, can also become superconductors. And the real question is, can you find a material with a critical temperature that's above room temperature? This would be a big scientific breakthrough, and there's still research going on in this field. This is a nice picture of barium crystal of benitoite, is barium titanium silicate. That's the blue crystals. And the black crystals are neptunite, which is potassium, sodium, lithium, iron, manganese, titanium silicate. This is a picture of barite, that's barium sulfate, and that's the white material, and fluoride, calcium fluoride, which is a purple material from Illinois, USA. This is a picture of France willite, which is a mineral of barium, lead, uranium oxide, vanadium oxide with water. The origin is Gabon in Africa. And this is a nice picture of barium chloride, BaCl2, crystals under the microscope. And it looks like a fractal generated from a computer program. That was today's video about the chemical element barium. Thank you for watching. Have a nice day. Bye bye.